Hello everyone. Today's lecture we will study a definition of refinement, and there are some standard result of upper sum and lower sum based on refinement. So let me define what is refinement. So definition of refinement. If P and Q are partitions of capital I, which is equal to a close interval a comma b, then Q is called as refinement of P if and only if P is subset of Q. So one should note that when Q is called as a refinement, then P should be part of Q. Then this means that Q is a refinement of P. So one should note that P and Q both are the partition of closed interval a comma b. So refinement is one of the partition. So to explain this in a better way, let me have one particular example. Suppose I have a set I which is equal to close interval 0 comma 1, and let me take the 3 partition P1 which is 0 comma 1 itself, P2 0 comma 1 by 3 comma 1, and P3 is 0 comma 1 by 3 comma 1 by 2 comma 1. Now you could see that here P1 is part of P2, P2 is a part of P3. So by transitivity, P1 is a part of P3. So P1 is a part of P2. From this I can conclude that P2 is a refinement of P2. Similarly, P2 is a part of P3 implies that P3 is part of P is refinement of P2, and also from the first and third P1 is part of P3, that would imply P3 is also a refinement of P1. So let me here I should write P1. So also P3 is refinement of P1 and P2, right? So I don't feel that refinement is really means it is not difficult to understand. It is one of the partition. Only thing is that it is for to define refinement you should have a two partition. Okay, so suppose I have a function, say this is my well defined function, bounded function defined on closed interval a comma b. So this is y is equal to f of x, and suppose I have a partition. So suppose let me define p is equal to x naught, which is equal to a x1 x2 dot 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 xn, right? So this is x naught, this is x1, this is x2 dot dot dot, here it is xn, this is xn minus 1. So let me draw a rectangle. So So upper sum basically I am finding. So upper sum means we have to take from the above, we have to draw a rectangle just above the curve. Now we can find out UPF very easily, that's not difficult. So UPF is basically a number, it is a sum of areas of rectangles which lies just above the curves. Now what I will do, I will define another partition Q. So suppose Q is a partition which is equal to my P union some extra point. So let's call me at y1. So Q is a partition which has P as well as it has some y1. So where does y1 belong? So y1 lies in one of the xi minus 1 comma xi. So where I goes from 1 to n. So you could see that P is a part of Q. So this means that Q is a refinement of P. So let us, where does Y belongs? Y1 is from x0 to x1 only. So it will lies in one of the sub-interval. So let me write down, suppose my Y1 lies in the second rectangle. So then if somebody asks me to find out UQF also, then how it will looks. Now you can observe that UPF has n rectangles, because 1 2, because x0 comma x1 will give me one rectangle, base as x1 minus x0. Similarly second rectangle, third rectangle, up to n rectangle we will have. But UQF, so area UPF has a area of n rectangle, so areas of the n rectangle. But if I go for UQF, then there is one extra point in UQF, because all rectangle will come and there is one more point, so I need to draw that point. So definitely extra rectangle has been added. So and I need to find out this. Oh, the upper one. So you could see that when I am forming UQF, see some of the portion is getting excluded. So this portion which I have shaded with the red part will not come in a UQF. So it will go out of the, in a calculation, it will not come. So it will go out of the calculation, that red portion. So adding a point in a partition, that means in a refinement, some of the area has been decreased. So you could see that UPF is always greater than equal to UQF. Let me add one more point. Suppose here some I add y2. So y2 is equal to, let me call it as q1 is equal to q union y2. So you can see that my q1 has area of n plus 1 rectangle. Now q2 has area of n plus 2 rectangles, and let me draw that also. So when I draw this, let me quite little clear in drawing. This is what my function is. So when I add one extra point y2, so this part will come, this part will come, but some of the portion will again go from the UQ to F, which I have shown from the red line. So that will go out of the picture. So you can see that UQF is larger than UQ1F. So on and so forth. So if I add extra point in a existing partition P, then the upper sum with respect to new partition becomes smaller and smaller. So that new partition basically is a refinement. So it will be very clear that it is very clear that refining a partition decreases the upper sum. That is very clear with the geometry because of this red part is going out of the picture. So this means that, let me write down in the next slide, refining a partition decreases the upper sum. Geometrically it is very clear, so we will not go in, means of course we will prove this mathematically also. So that is our next result. Prove that if Q is a partition, if P and Q are partition, and if Q is a refinement of P, then UPF is greater than equal to UQF. So that we will prove in next. That is our next target. Now we will prove a result, that is refining a partition decreases the upper sum. So let me write down that result. So let f be a function from I, which is equal to close interval a comma b, to r, be a bounded function. Let P be any partition of AB and Q is refinement of P, then prove that UQF is less than equal to UPF. Okay, this is my target. So let's prove this theorem. Proof. So P is any partition of closed interval a comma b. So let's take P as x0, which is a, x1. Generally I write a is equal to x0, but anyway it doesn't matter as such. So x0, which is a, x1, x2, dot 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 xn is equal to b. Be any partition of close interval a comma b. And now let me take a partition Q. Q is a refinement, so Q is a refinement of P, so it is very clear that Q will or P is fully contained in Q. So Q has P as well as some extra points. So let Q is equal to P union y1, y2, dot 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 ym. So it's very clear that you can observe that P is a subset of Q. So that means Q is a refinement of P. Now what I have to prove? I have to prove that UQF is less than equal to UPF. So to prove this result, I will consider the case that just add one extra point in a P and see the effect of adding one extra point in P. How does affect on a upper sum? So we will observe the effect of adding one point in P. So that is, let Q1 is equal to P union singleton y1. Now you can see that P is a subset of Q1 So implies that Q1 is a refinement of P. So this would imply Q1 is a refinement of P. Now let me visualize it geometrically also. Suppose I have a F which is to A. Suppose somewhere I have xk minus 1 and this is xk, so on and so forth. So let me draw a rectangles. So here xk maybe xk minus 1. So right. So upper sum means above the curve. I have to find out the rectangle. Now what I will do, this x0, x1 dot 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 up to xn, these are the point of from the partition P. So for Q1 I need to add point P y1. So let me add y1 over here between xk minus 1 to xk. So let y1 belongs to, now I will say open interval because it cannot be xk nor xk minus 1. So y1 belongs to xk minus 1 comma xk for some k between 1 to n. Right. So UPF has n rectangles, area sum of areas of n rectangles, whereas UQ1F, if I add, since Q1 has n plus 1 point, means n plus 1 rectangle, so let me draw a rectangle with respect to this. You can see that maybe this should come and this will come. So you can observe that this extra part will go out now. It will not contribute anything in the UQ1F. But adding this extra point in UQ1F, you will have n plus 1 rectangles, whereas UPF has area of n rectangles. So let me define supremum infimum. So let capital MK is supremum of fx such that x belongs to xk minus 1 comma xk, and let me have on this rectangle I will have another supremum, and this rectangle I will have another supremum. So let me call mk dash is a supremum of fx such that x belongs to, I will say xk minus 1 comma y1, and mk double dash is again supremum of fx in x belongs to y1 comma xk. Now I need to find out the relation between mk dash and mk double dash. Now you can see that where does mk geometrically lies? Here with my mk dash and mk lies over here, whereas my mk double dash is somewhere here. So cross से दिखाया है. So you can see that mk is always greater than equal to mk dash as well as mk double dash. So mk is always greater than equal to mk dash, and let me write down in a more precise well, and So mk is always greater than equal to mk double dash also. So the reference for this, let me call this as number 1, this both inequality as number 1. To understand this in a more better way, I will just ask you to do one small exercise. If you have a two sets, finite sets, suppose, which are bounded above means it has a supremum, and if A is subset of B, where A and B are bounded above set, then its supremum of A is less than equal to supremum of B. This is what the result is. Now here you can see that P is a subset of B, P is a subset of Q1, then supremum of P, that means not P, I will say, over the rectangle, that xk minus 1 comma xk is definitely less than equal to supremum taken over your xk minus 1 comma y1 and y1 to xk, right? That one can generalize or can visualize. So I will be using this one later on, so let me just label this as very important inequality for me. So now let me consider u, I will consider uq1f, uq1f. uq1f is nothing but capital M1 x1 minus x0 plus capital M2 x2 minus x0 plus dot dot dot, that mk dash y1 minus xk minus 1 plus mk double dash xk minus y1 plus dot 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 mn xn minus 1. Right. So these are how many terms these are, which I have underlined. These total n plus 1 terms I have, because there are n plus 1 rectangles will form in uq1f, and those areas I have noted down. Well, I will be using this one, that mk is always greater than equal to mk dash. Similarly, mk double dash is greater than equal to mk. So now here this mk dash and mk double dash will be replaced by uh, everything that equal to becomes now less than equal to m1 x1 minus x0 plus m2 x2 minus x1. I did mistake here, so let me modify that mistake. Plus, you can see the third term is m3 x3 minus x2 plus so on and so forth. So now here this mk will be dash will be replaced by mk, and this mk double dash will be also replaced by mk. So in a bracket I will take that mk common, so I will have y1 minus xk minus 1 plus xk minus y1 plus dot 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 dot, I will have mn xn minus 1. Now you can see that this y1 and this y1 will get cancelled, so I will have xk minus 1. So let me write down in a next. So I will have uq1f is less than equal to m1 x1 minus x0 plus m2 x2 minus x1 plus, this is now mk xk minus 1 plus that mn xn minus 1. You could see that these, now whatever underline I have done, these are the n terms basically. So this actually contributes, so this is same as summation I goes from 1 to n capital mi xi minus 1, and which is your well defined UPF. So what I have proved is that UQ1F is less than equal to UPF. This is very important. So let me write down in our next slide. So what I have proved, UQ1F is less than equal to UP1, not P1, UPF. So Q1 is a refinement of P, though Q1 has only one extra points than P. So between, if I apply this rule, then UQ1F is less than equal to UPF, that we have seen. Now let me take Q2 as Q1 union Y2. In other words, you can see that Q2 has all the terms of P and two extra points, that Y1 and Y2. So this is same as P union Y1 comma Y2. Well, this I don't want to see now, because just I won't be using this, but then you can clear that it is very clear that Q2 is nothing but like this. So it's very clear that Q2 is a refinement of Q1, because Q1 is subset of Q2 and P is also a subset of Q1. But then I don't need P now, so I don't want to disclose that, because that's fine. So Q2 is a refinement of Q1, and just one extra point Q2 has, because Q1 में जितने point है उससे एक ही extra point है. So this would imply Q2 is a refinement of Q1. And since it is refinement, let me write down this as a star. So I will apply this star over here. So now here my Q2 is a refinement of, if Q1 is a refinement of P, then UQ1F is less than equal to UPF. Now here, if Q2 is refinement of Q1, then I will have UQ2F less than equal to UQ1F. So from star. Similarly, I can add one more terms which is not necessary actually, but let me write down one more step for clarity. So Q3 similarly, 3 lines with Y stands for similarly. Q3 is equal to Q2 union Y3. Right. So Q2 is a part of Q3. Now what Q3 has? Q3 has everything of Q2, only one extra point. So basically, in terms of P, if I want to refer, this is same as P union Y1, Y2, Y3. Right. So this would imply Q3 is a refinement of Q1, and then apply star on this. So apply star. So if I apply star, so now let me go to the star. Now in star, Q1 is a refinement of P. जो refinement वाला होता है वो पहले आता है और जो original है. So here Q3 is a refinement. So I will have UQ3F is less than equal to UQ2F. So continue in the similar manner. If I continue in a similar manner, somewhere I will have Qm, which is equal to Qm minus 1 union Ym. And now you can see that Qm minus 1 union Y1, basically it is P union Y1 Y2 dot 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 Ym, and this is basically my Q. So UQM is same as Q. So then apply star. So Q is refinement of Qm. Qm minus 1, because Q and Qm are same. Then by star, I will apply star on it. Then I will get UQF is less than equal to UQM minus F. Right? So if I cover all this inequality, then this inequality, then then this equal uq2f is less than equal to uq1f, then this. So if I club all this inequality, what I will be having, I will have a nice chain. I will have uqf is less than equal to uqm minus 1f, which is less than equal to uqm minus 2f, less than equal to, so on and so forth. So this is less than equal to uq3f less than equal to uq2f less than equal to uq1f less than equal to upf. So by clubbing all this, I will get, so finally I will have uqf and upf follows the less than equal to notation. So uqf is less than equal to upf. This completes the proof that refining a partition decreases the upper sum, because this is a partition का, अगर you upper sum का partition किया तो refinement वाला part decrease होता है upper sum में. So hence I said refining a partition decreases the upper sum, because upper sum is a number, so upper sum decrease होता है. On similar line we will be proving a result of refining a partition increases the lower sum. Lower sum, the case changes. So that result we will prove in an upcoming lecture. Thank you.